So in this video, I'm going to walk through yet another example of how we can use the torque-angular momentum relationship in order to generate equations of motion. So in this problem here, we have a semicircular bowl on top of a cart, and we have a particle that can roll around here. That's particle is P, and it has a mass of M. Now, we can go ahead and start defining reference frames. So we have our fixed frame A, A1, and A2. And to follow along in the notes, I called the origin of that frame Q. And then we defined another reference frame B to keep track of the rotation of point P here. And so we'll call this is of course frame B, so B1 and B2. And the origin of this frame I called O. And keep in mind here, if this is, you can think of this as the A1 direction, our theta is this here. And so what that means is that theta in this case is negative. So that means our angular velocity is equal to negative theta dot B3. And lastly, this distance here, that radius of this bowl is R. Now we start by defining the degrees of freedom of this system. So here we technically have two. So we have theta, and then this position of this cart can change, right? So we call that x. So we have 2 degrees of freedom. And our coordinates are theta and x. However, one thing you should keep in mind is that in the problem statement, it says that x double dot is known. And in fact, we set x double dot equal to a. And so what you'll see is that eventually when we get to our equation of motion, right, typically if you have 2 degrees of freedom, you need 2 equations because you have 2 unknowns, 2 coordinates, x and theta. But because one is known, so because we know x, or what you'll see is x double dot, we're ultimately only going to need 1 equation of motion. And so that's just to simplify your lives a little bit in this example. And this appears in the homework as well. So like I said, I'll go through this example here, but if the consequence of x double dot being known becomes a source of confusion, just let me know and we'll review that. Okay, so the only actual mass that we have in this problem is the particle P, right? We actually, we're just pretending that the cart is massless. So that means on our free body diagram, we only need to care about the forces acting on our particle P. So we have our gravitational force, plus we have our normal force, right? So in the B1 direction from being in contact with the bowl. So now we just simply push forward and plug in all the terms we can in our torque angular momentum equation. So as a refresher, again, that equation is that we have the torque of point P about point O. So again, we're going to calculate this with respect to point O, the origin of our B frame here. So our torque is equal to the derivative of our angular momentum of P about O plus the velocity of point O in frame A crossed with the linear momentum of point P in frame A. So the first thing we're going to do is calculate the torque. So again, torque of point P about point O is equal to ROP crossed with our force vector. Now ROP is equal to R in the B1 direction. And according to our free body diagram, force is equal to negative mg in the A2 direction minus N in the B1 direction. So we can write torque as being RB1 crossed with negative mg A2 minus NB1. Now remember that we, when we take this cross product, that we can distribute this terms here. So we'll get torque is equal to RB1 crossed with negative MGA2 plus RB1 crossed with negative NB1. And this last term, because both are written in terms of B1, goes to 0. And so what we're left with is calculating this cross product here. And again, we are left with taking the cross product of, we have two different reference frames here, right? So we have R and B1 and negative mg and A2. So we're going to put everything in terms of the A frame. So that means we need to have an expression that relates B1 and B2. Now, this is important to remember that we have a negative angle. And that's key here because now our relationship says that we have cosine theta, negative sine theta, and cosine theta. So the negative sign of the sine theta switches to what would be the case if we had positive angles. And so make sure to check out the notes on coordinate frames if this is unclear why. But that's important to remember. Okay, so now we can write the this B1 in terms of A1 and A2. So we have the torque is equal to R, and here we have cosine theta A1 minus sine theta A2 cross with negative mg A2. And so we can again distribute this, so we get R cosine theta A1 crossed with negative mg A2 plus R negative R sine theta A2 crossed with negative mg A2. And again, you have two A2 terms, cross product between them, so this whole term goes to 0. And so what we're left with is m, so we have negative mg r cosine of theta, and then A1 crossed with A2 is going to give us A3. And so this here is our torque term. So now that I've cleared some space, we can now write out our second term, which is the derivative of the angular momentum of P about O in frame A. So we start by just first calculating the angular momentum. And that is equal to ROP crossed with the linear momentum of P in frame A, which we can write out as ROP crossed with M times the velocity of point P. So we have our ROP vector is equal to RB1. And then we have our velocity vector. But our velocity vector, it's important to remember that when we take the velocity of point P, in frame A, we're actually taking the time derivative of RQP, right? So from the origin of frame A, so from this Q. So RQP is equal to X of A1 plus RB1. So we need to take that derivative of XA1 plus RB1. So now the velocity is going to, we can separate this out. We know that the derivative of XA1 is just X dot A1 plus, and then here we use our magic formula. So we take the time derivative in frame B of RB1 plus, and this is the angular velocity, which we said over here was negative, so I could just write this as a negative term, times, or cross with RB1. And that means we'll ultimately get the following, that the velocity is equal to X dot A1, and then we have minus R theta dot, and B3 crossed with B1 is equal to B2. So now we can go back and plug this in. So for our angular momentum term, we have ROP, so that's RB1, crossed with M times X dot A1 minus R theta dot B2. So of course we're going to have to distribute this out. So we can write now our angular momentum as RB1 crossed with mx dot A1, and then this is plus RB1 crossed with a minus R theta dot B2. And I forgot to put the little m in there. Okay. So now we have to, again, take this B1 and write it in terms of A1 and A2. So we did this, the exact same thing in the last term. So we wrote that B1 is equal to cosine theta A1 minus sine theta A2 cross with mx dot A1 plus, and then here we have, this ends up being a negative mr squared theta dot, and then B1 cross with B2 is equal to B, that's a 3 there. And so again, if we distribute this out, we get that R cosine theta A1 crossed with mx dot A1 minus R sine theta A2 crossed with mx dot A1 minus mr squared theta dot B3. So this term, because you have the cross product between two A1s, that ends up going to 0. And then we can write here the angular momentum is equal to, we have a negative mr x dot sine theta, and then we take the cross product between A2 and A1, and that ends up being negative A3, so we're going to write A3, and then we're going to get rid of that negative sign. And then we have negative mr squared theta dot B3. And so you can combine these terms because, again, A3 is equal to B3. And so I'm just going to now write this over here because we have to take the derivative. So we're going to take now the derivative of our angular momentum term. So we're going to take the derivative in frame A. So I'm just going to write this all in terms of A3 to make our lives easier. Minus mr squared theta dot, oops, and that's all in terms of A3. So we can write this then as d e dt. I'll just write the equal sign because I'm going to start running out of space here. So we can set that equal to. All right, and so here we have, we use the product rule, so we're going to get m r x double dot sine theta a3, and then we get plus mr theta dot x dot cosine theta. And then we take the derivative a3, and then we take this, the derivative of this last term here, and so this is negative m r squared theta double dot a3. So ultimately this right here is our derivative term. So now I'll just write this out nice and clear the space for you. Okay, so now we need to get our last term here. So that's v, the velocity of point O in frame A, crossed with the linear momentum of point P in frame A. So we can write that out as the velocity of point O crossed with mass times the velocity of point P in frame A. So to get the velocity of point O, we first we have our position vector from Q to O, and so that is equal to xa1. So we just simply take the derivative of that to get x dot a1. And then we need to get the velocity of point P. We get the position vector of RQP, and that's equal to xa1 plus rb1. And then earlier we calculated, sorry, this should be an O. Earlier we calculated that VP, we calculated this derivative. So this ends up being x dot a1 and then minus r theta dot b2. So we can write that this term here, sorry, velocity point there. Okay, so we can write this out as x dot a1 crossed with m times x a1 minus r theta dot b2. So now we can distribute these terms, or distribute that m, and then distribute the cross product. So we end up with x dot a1 cross with m x dot a1 plus x dot a1 cross with m negative mr theta dot b2. So we have this a1 cross with a1 term, which then goes to 0. Then we have, of course, an a1 and cross with a b2 term, so we have to actually transform b2 and write that in terms of a1 and a2. So again, we refer back to this relationship here. So we have cosine theta, negative sine theta, sine theta, cosine theta, and that's A1, A2. And again, this is because we have a negative angle. So we can now write out this expression for B2. We can plug that in here. So this will give us x dot A1 crossed with a negative mr theta dot, and then B2 is equal to sine theta A1. Oops. Oh yeah, I'll just plus cosine theta A2. And now we'll distribute out this cross product, right? So we'll get x dot A1 crossed with negative mr theta dot sine theta A1 plus x dot A1 crossed with negative mr theta dot cosine theta A2. Yet again, we have an A1 crossed with an A1 term, so this is going to disappear. And so what we have left, I'm going to write this out here in its original form. What this ultimately equals is we have negative mr x dot theta dot cosine of theta, and we have A1 and A2, and so that's going to give us a negative A3, or that gives us a positive A3, so then we just write it like this. And then here, what we're left with is the answer for this cross product term. So now we just have to go ahead and plug everything in. So now that I've again cleared out some space, we just plug in these terms. So our torque is equal to negative mgr cosine theta A3, and that's equal to our derivative of angular momentum. So we have m x double dot r sine theta A3 plus mx dot r theta dot cosine theta A3 minus mr squared theta double dot A3, and then we have our cross product term, which is negative mx dot r theta dot cosine theta A3. So these two terms here cancel each other out, and so what we're left, and we can cancel out a few other things while we're at it. We can get rid of the m's, we can get rid of some r's, and so now we can get rid of the A3s, right? And so one key thing is here, right, we could have written that in terms of B3, of course, no matter where it happens, either here or in prior steps, right, equating A3 and B3 will help you put everything in the same frame and help you eliminate some terms. And so then what we end up with is negative g cosine theta is equal to x double dot sine theta minus r theta double dot. Now again, this is where that instruction that x double dot is known comes into play. Right? So typically we would, if we didn't know what x double dot was, we have to generate a second equation in order to solve this, right? Because we would have two unknowns, right? We'd have theta and its derivatives as technically an unknown, and then we'd have to have x and its derivatives. But because, again, we know that x double dot, or we said in the problem statement that x double dot is equal to a, what that means is that our equation of motion can now be written as, and I'll write it in this way. We can say that r theta double dot is equal to, oops, sorry, not equal to, and then we have minus g cosine theta, and then minus a sine theta is equal to 0. And then this here is our equation of motion. So this is, again, just another example of how we can use that relationship between angular momentum and torque to get a equation of motion. All right, so this should be essentially just another tool in your toolbox for relating force and motion together. And as we do problems, especially in this week's homework, I'm going to have you solve for equations using this angular momentum and torque equation as well as the force and linear momentum equation, so you can get a feel for what you think is easiest for certain problems.